Good morning, everyone. It's Rob Timmings from ECT for Health, again here with another Knowing Your Jargon. This is the last video in our literally 9-part series. So video number 8 of our 8-part series looking at respiratory physiology jargon. This last session is looking at a term you may or may not have heard in clinical practice called a VQ ratio or a VQ mismatch. Either of those terms. Many nurses and paramedics have heard the term VQ when being referred to a particular type of nuclear imaging scanning that we can do when we're looking for a pulmonary embolism. A VQ scan is a thing that we can do, and there's some sort of similarities. Certainly the abbreviation VQ means the same. So let's get straight down to it. VQ. A normal VQ ratio is a mathematical ratio, as you can see from the abbreviation V ratio to Q is exactly the same as saying V divided by Q. And a good way to remember V divided by Q is to actually draw the picture of what it is that we're describing when we're looking literally at a VQ ratio. So let's start. We've got ourselves the alveoli, and this represents all of the air that you bring in and you bring out over a set period of time. So let's say over the course of X amount of time, you started the clock and you start breathing in and out. And then after a period of time, let's say a minute down the track, you stop the clock. You could have measured all of the air that you breathed in and out, but particularly the volume that you've breathed in that period of time. And that would be called your ventilation volume. That's the V part of the VQ. The other bit of the equation is looking at the blood that literally circulates through your lung. So we've got that capillary that represents all of the blood that circulates through your lungs. So as blood is circulating through here, and it's circulating from the right side of your heart through your lungs to become oxygenated, to dump the CO2 and back to the left heart, gas exchange is taking place. Now this is the perfusion quotient. Perfusion quotient. For reasons that I don't understand, the P is not used, which leaves us with just the Q. So now I have a V over a Q, a V over a Q ratio. So what's considered to be normal? Well, over a set period of time, if you were to bring in 4 litres of air, and that set period of time might be, say, a minute. In that same period of time, through your lungs, you have perfused about 5,000 mils of blood. So 4 litres of air is coming into contact with 5 litres of blood. That, expressed as an equation, is 4,000 divided by 5,000. We can simplify that by saying 4 over 5, or 80%, is the answer to that mathematical equation. And that brings us out to what the actual VQ ratio is, reduced down to a decimal. A normal VQ for a human adult lung is 0.8. That's our normal. Now I know that was a few minutes of your life that you'll never get back, but let's translate that through to clinical practice. If you have a VQ ratio that is elevated, a high VQ, so a number that is larger than 0.8, or if you have a VQ that is lower than 0.8, a low VQ, then you are not going to be oxygenating your blood adequately. And for that reason, respiratory failure can be diagnosed with a high VQ or a low VQ. In those circumstances, the ventilation to perfusion ratio, the V to Q ratio, are said to be mismatched. Normal VQ ratio is 0.8. So let's look at a couple of examples. We're going to start with low VQ ratio. So in a low VQ ratio, we've got this patient, they've got a lung, they've got a capillary or blood that's perfusing their lung. We've got a normal volume of blood travelling through in a set period of time, but for whatever reason, let's say this patient's lungs have started to fill up with fluid. There we go. We'll even put a little fish in there. Of course you don't have fish in your lungs unless you've got a serious case of aspiration. But in a situation like pulmonary edema, where plasma starts to leak out of these capillaries and starts to fill up this interstitial space, and then starts to osmose into the alveolus itself, we've literally started to displace the area that normally is reserved for air to come in and out with fluid, with liquid. In cases of pulmonary edema, I might only be able to bring in 3,000 mils of air to come into contact with 5,000 mils of blood. In those circumstances, you would say that there is a ratio of 3,000 to 5,000, reduced again mathematically to 3/5, which is 60%, which is the same as saying 0.6. When somebody's got a low VQ ratio and it sits down around 0.6, you can see that there is less molecules of oxygen coming into contact with the blood that travels past. So blood is said to shunt through the lung and not become oxygenated. In that regard, a low VQ is sometimes referred to as a VQ shunt. And you may hear the doctor talking about the patient's got a VQ shunt when they have pulmonary edema. That's one example. Let's have a look at an example of a high VQ. Again, we use the same image. I'll rub that stuff off the top. We've got our alveolus in this circumstances. We've got our capillary perfusing the alveolus. There it is. Again, blood is coming through from the right heart and it's going off to the left heart. The premise is that oxygen should be diffused across this space. Now in this circumstance, when somebody's got a high VQ, what we're actually looking at is not a problem with the air getting in and out, but a problem with the amount of fluid that's getting through. So this patient has a branch of blood vessels that are blocked with some clot. Let's call it pulmonary embolism. This patient's got a pulmonary embolism, and there is a blood clot in some of those blood vessels perfusing some parts of the patient's lung. Over that period of time, the patient might be able to breathe in and out their 4 litres of air, so there's no problem with the ventilation side of the VQ equation. But because there is a blockage in a network of blood vessels that normally perfuses all of those 700 million alveoli, we've actually now got a reduction in perfusion. So the Q part of our VQ ratio is reduced. Let's say only 4,000 mils of blood was able to perfuse through in the same period of time that it took to breathe in and out 4 litres of air. We've now got a ventilation to perfusion ratio that is 4,000 over 4,000, which reduced is 4/4, which mathematically is the same as saying 100%, and as a decimal is 1.0. Can you see that with a VQ ratio of 1.0, it's higher than the normal VQ ratio, which you'll recall up here was 0.8 is what's considered to be normal. When a patient's got a VQ ratio of 1, then they've got what's called a high VQ, and this is sometimes referred to as dead space ventilation. In other words, my patient is bringing air, oxygenated fresh air, into an area where there is a decrease in blood moving through because of some sort of a clot, like a pulmonary embolism. So there we have two examples of VQ mismatch. The calculation of the VQ ratio, just reflecting on that, coming back to this over here, is the amount of air coming into contact with the amount of blood over a set period of time. The low VQ is sometimes referred to as a VQ shunt, and that's where there is less air to blood. And a high VQ is the opposite, that's where there is less blood to air. And both of those consequences are going to be a decrease in the amount of oxygen that gets into the arteries. So my patient's PaO2 is going to be reduced. Now, just reflecting back on video 6, if your PaO2, which normally sits 80 to 100, is reduced and it is less than 80, we're going to call that hypoxemia. If, however, it is less, that's a wrong symbol, isn't it? I've gone backwards with my symbol. I always do that with the symbol. Less than 80. If it is less than 60 millimeters of mercury, then this hypoxemia is so profound that we would actually refer to that as respiratory failure. And that in a nutshell is our VQ, understanding the VQ ratio, understanding the complication that is VQ mismatch, part 8 of our, well, it was actually a 9-part video series. Hope you caught them all, hope you enjoyed them, love to get your feedback, love to get some comments. You'll find them all on YouTube. I've posted them up on our Facebook page as well. Feel free to share them, share the love. Next up, we're going to have a look at blood gases. So have a look at that blood gases series coming up soon. See you later, guys.